All right, so we're recording now, and I unfortunately forgot to record the previous meetup, so this one will serve for both sections for the recording. So thank you everyone for attending, and we have a few things to go over. I want to go through homework. I want to go through the second project. So looking at data shader and dealing with big data in Python, and we'll go over Shiny as well. And for Shiny, I mentioned that I was going to post a video, but the video that I had was a bit outdated, and I figured that I'll just use the time in this meetup to go through a few points on Shiny. So so we'll sort of use this to go through some concepts of building these data-driven web apps. So let me plug myself in, and so with that, we'll just get started. So so in terms of the homework, how did everyone find it? Was there did it seem was everyone glad to use a tool like this? Were there any sort of challenges? Um, what was everyone's experience here? Cool. So the yeah, so Dubar. That's pretty much like what I was going for with the project like this. And Georgia, you mentioned that you're sort of fairly new with Python and Plotly. The so with Python, I wanted to focus a bit like at least equally on Python and R, which pretty much I am doing in this course. And the like I found that a lot of the courses, it's a bit more R centric, and I think it's good to have a balance in terms of these two languages, and it'll be good for you guys to kind of have exposure to both. But yeah, I'm glad people thought that that enjoyed what you were able to do with tools like this. And so really like what the goal of this assignment was to really sort of get at kind of aggregation concepts, dealing with big data, so binning and aggregation, and trying to arrive at these concepts in a slightly more manual way, being able to kind of bring in the data, and given a question, decide what is the best way to aggregate and visualize it. So the first question was more, kind of using traditional, more traditional visualization packages, and how, how kind of what you would want to, like what kind of strategies you would use to view large data sets. And with Data Shader, Data Shader is just a really cool package, and it's, really I mean, I just thought it was really useful to have you guys exposed to Data Shader. In terms of, so yeah, Kumujini also mentioned that that she was a bit new to Python. In terms of the notes, did people find the notes within the notebook useful? Or were there any other functions that, yeah, George, I'm glad that was useful. Yeah. So so I tried to kind of, write it from the point of view of, sort of moving from R to pandas, and, so trying to kind of keep those analogs. Um, And were there any other functions that it might have been helpful to include, or anyone anything anyone could think of?
I would say the offline plotly.
Yeah, I so I saw that in the discussion boards, and I didn't yeah, that was just something I didn't catch because I'm just so used to having my Plotly account. And just for future, I'll make sure that obviously for future assignments and in the future when I'm teaching this to be more clear about it. Plotly offline is definitely something that you're able to use, and also anything that we're doing in Python is like you could use a free Plotly account, and it's so you don't have to you're able to just sign up for a community account and use pi.iplot the way that I was. So obviously there's like you could get by with just sort of using either the open source offline version or just a free community account. Um, but I did notice that a few students were having issues with that, so I apologize for not making that a bit more clear. So so yeah, in terms of that, this is kind of meant to really serve a lot of purposes, like really uh, get students a bit more acquainted with Python, and then also to so to kind of serve as the Python data visualization project, and also to really get into strategies to deal with big data. So this data set, the Pluto tax lot data, it includes every single tax lot in New York City. So definitely a larger data set, and something that's kind of unwieldy to deal with unless you're really thinking about what you want to do. And it's as I sort of um, kind of hinted at when we were first looking at it, it's a kind of there are a few um, errors in the data set. So kind of the first look at this data set when we're just bidding by every year and just trying to get an idea of number of lots built, we end up with something weird looking like this, where we have kind of these random spikes. So did anyone catch why that is, or either catch in the documentation, or kind of guess why something like this is happening? So so it's mainly happening with these earlier years, and you could see that things are clearing out, a bit when you're looking at later years. It kind of things look a bit smoother. And what's happening is, someone just chatted. Yep. So yeah, Dubar, you're absolutely right that this has to do with buildings being labeled within the decade. So when you're looking at older buildings, especially kind of older, nondescript buildings, the records could have been lost. The records could just not be accurate, and and all that's known is the closest decade that the building is built. So there's and actually in the documentation you'll see that there's a few caveats that they include. Things like I believe the after 1900 data is accurate within the decade. Before 1900, I think there's a large number of buildings that are just simply grouped as being built in, yeah, like 1899. You could see there's a spike there, so that's sort of this is a building that's more than 118 years old, but we have no clue when it was built, so we're just going to stick it in 1899. So there's a few, there's kind of a few weird things going on. And so, part of what I hinted at is, you're going to have to find ways to deal with these sorts of data issues. So let's look at sort of what we're asking with the first question. So we have a series of building collapses, and we're trying to investigate older buildings for safety. And what we're particularly worried about are buildings that were unusually tall when they were first built. And so what this is sort of getting at is, as time is going on, you're developing new building technologies, and you're able to build taller buildings as a result. But as you're building these taller buildings, the first few times you try it, there's still, you still haven't really arrived at best practices for building buildings of that height. So it's, there's sort of a difference between a skyscraper that was built in, the 1900s versus, or, very early 1900s versus more modern skyscrapers. So, really what we're looking at are, kind of these older buildings, and, when buildings really first got high. And so, the best way to look at, so, there's, really what we're looking at is, and I sort of hinted at this, that, we should be grouping buildings by these different heights, and, try to get an idea of when were these types of buildings first built in large numbers. So first of all, we want to try to get an idea, not a more detailed, that's poorly worded, but get a clearer idea of how buildings are built over time. So first, we're just going to downsample what we're looking at to kind of solve this issue here, because really something like this is pretty, it really throws off everything. It makes like visually, you think that there were more buildings built in 1930, like vastly more buildings built in 1930 than in any time past the 80s, when really what's happening is it's just kind of clustered. And when we disaggregate it, so here I just used I'm using some built-in pandas resampling functions, and I'm just looking at every 5 years. There's still some spikiness, but it's way less than what we were having with the annual data. And so looking at something like this, we're able to get a bit more information about what's happening. So you could see that you have, you have a building boom happening kind of during the Roaring '20s, that falls again during the Great Depression. But even then, like, there's a large portion of the city that was built sort of earlier on, and really this is the period when the city is really expanding, and so there's a large number of buildings that were built in this time period, and so things taper off in later years, and you kind of notice a little kind of hump here when we're looking at the build up to the Great Recession, and then really sort of things going down is just sort of we're looking at more recent years. So looking at something like this, you get an idea of when these buildings were built. But let's take another look at what this question is asking. So we're looking at sort of buildings like that were kind of unusually tall when they were built. So we're sort of looking at kind of the first few buildings of a specific type that were built. you could kind of get an idea with something like this. You could sort of see that, there's obviously, um, buildings built earlier on are going to be sort of the first few buildings built of a specific type. But you have things like you have these spikes here, and this really isn't referring to, all this is referring to is kind of when there was an uptick in the rate of buildings getting built. So one approach is to look at is to, rather than looking at kind of how many buildings were built in each period, looking at this data cumulatively. So get it as sort of starting from the beginning of our data set, and then kind of going forward in time, and sort of building a tally of buildings that sort of are built over time. So there's another built-in function that you could use for that, cum sum here, and that's just getting the cumulative sum. In addition, I'm just making it a percentile. So rather than looking at numbers of buildings, I'm looking at percentages. And this has the added benefit of I don't really have to worry as much about the kind of spikiness with the years. So here, the looking at the 5 and 10 year spikes really threw off visually what was happening. Whereas if I'm looking at it cumulatively, it kind of throws it off. It makes it look like a stepwise function rather than a smooth function. But because we're increasing over time, you're not losing as much information. So you could, the way that you could really notice that is if you're looking at the period after the 1980s when things smooth off, you're not, that looks like it sort of continues on from what's happening beforehand. Whereas with this, it looks like there's fewer buildings built in each of these years than there are in kind of the these spiky years. So you end up kind of with a more truthful visualization when you're looking at it in that way. So this is looking at all buildings in the data set. And something like this, if we're and another benefit of looking at these percentages is this lets us, I like in the question, I didn't really specify what it means for buildings that were unusually tall, when they were built. So a graph like this lets us choose what we want our cutoff to be. So if you wanted something like 50%, if you want to say we want to find the first half of buildings that were built and really target those for inspection, you could pretty easily just sort of highlight over a sort of get a range that would be happening at. So here this is happening around 1930 if you're looking at all buildings grouped together. And something like this also really is useful when you're looking at various groupings of buildings. So I ended up just faceting the data to get an idea of different story groupings. So 0 to 10, 10 to 20, 20 to 30, etc. So for each of these groupings, we're able to look at, we're able to choose our cutoff, whatever it is that we're looking at, and get a measure. So for buildings that are 0 to 10, we're again looking around 1930, get similar values with 10 to 20, but for 20 to 30, we don't hit 50% until around the 60s. So if we're looking at buildings that are built in in 1950, we would only really check them if they were above 20 stories. And also, with taller buildings, you're getting the pattern of buildings getting taller over time. So you're hitting that 50% measure, in the 1980s when you're looking at 30 to 40 story buildings, and even a bit later when you're looking at taller buildings. Um, so in terms of what most students ended up doing with this question, most people got most people arrived at uh, or not most, it was around half, I guess, that sort of used faceting as a way to look at this. One issue with this sort of data set is the distribution of the types of floors. So we're looking at every single building lot, every single tax lot in New York, and there's going to be a lot of shorter buildings. A lot of, each townhouse is going to count as a tax lot, whereas, an apartment building, it's housing more people, but it only counts as one lot. So the data set is definitely skewed, left skewed towards the shorter buildings. You're going to get a lot of, a lot of 2 or 3 story townhomes. You're going to get a lot of single family homes. You're going to get a lot of tenement buildings, so sort of older apartment building, like walk-up buildings, buildings that are usually around 6 stories. You're going to get a lot of those, and this affected a few. This kind of limited what sorts of strategies you could choose in visualizing this data. So a few students, for example, chose to use bar charts to look at buildings being built over time, and something like using bar charts really resulted in the data getting overwhelmed by this 0 to 10 story grouping. So if you're so imagine if you're looking at stacked or grouped bar charts, you would have that just be overwhelmed by 0 to 10 stories, and then kind of not really see the detail that's happening with taller buildings. And a few students had ways around this. So, choosing different scales, choosing a log scale was one option. Some other students ended up just sort of removing those 0 to 10 stories and looking at the building grouping separately. And that I didn't really those all were sort of valid ways of looking at something like this. But if you're what we're doing here is we're really normalizing the data, and we're by looking at it in this way, we're using a similar comparison. So this 0 to 10 story grouping here, this is still the overwhelming, sort of overwhelming the data set, but we're not seeing that because we're only looking at percentiles. So we're able to compare things sort of on their own merit. So really those were the main concepts that I was getting at with this first question. That sort of what sorts of things should you be thinking of when you're aggregating data sort of going through the process of aggregating data manually to find out what you should be doing, and sort of what strategies are available to kind of how you could end up with visualizations that don't make sense if you're aggregating in the wrong way. So if you're aggregating over time in the wrong way, or if you have this uneven groupings and you still want to you're sort of asking a specific question and you don't want to have the weird groupings change what you're looking at. So for question one, does anyone have any more questions on that before we move on to the second question?
Basically, my approach was actually to plot in 3D,
Hmm.
having a year, number of floors, and the quantity as my Z. That was my approach.
Hmm. Yeah, I saw. Actually, you weren't the only one who chose that, and I was. Uh, that was actually surprising to me that that quite a few students ended up choosing 3D 3D visualizations. You so that was that was definitely a unique way of viewing the data, and if the data were a bit more evenly distributed, it would have it actually would have allowed people to sort of allowed a viewer to glean a bit more information than you would using 2D visualizations. But but because um, like the 3D visualizations did end up falling prey to the sort of uneven distribution. So what you found with those sorts of graphs was you would have the you would just have so much more. The points would be sort of so much higher for 0 to 10 stories than it would be for the others.
Yes, absolutely. I found that problem and I tried to figure it out how to make it look better,
Mm-hmm.
but I couldn't do a better cleaning process on that idea.
Mm-hmm. Mm-hmm. Yeah, something like that is definitely is definitely useful for kind of more comparable. Like I believe um, in the 3D discussion, I sort of mentioned like yield curves as an example of something that you showed 3D, and it's that's something where it's comparable across all three of those dimensions, and it results in something that really provides um, more information. So like, um,
Yes, basically the idea I got it from the article from the New York Times that we read.
yeah,
Uh,
yeah, this one that it's comparable. So it's here you're sort of really getting more information than you would otherwise, and it's something like this. Like I've worked with clients who in some previous jobs where you're they're really weren't like this really is a better way of looking at yield curve information than a lot of the alternatives. So yeah, definitely interesting to see kind of unique spins on it, but unfortunately, there's still some issues with the data set that kind of prevented something like that from being as useful.
yes, I realize now.
Yep. Cool.
Could it have
Uh,
been so that we ignore the first 10 floors data and proceed with the rest of the floors and then use a 3D? Would that make sense? Or that's not the right way to do?
I mean, so a lot of students definitely chose to use that approach as well, and I mean, like with any of these questions, there's not like this isn't the only correct answer. Really, what these projects are meant to do is sort of highlight different pitfalls in dealing with different data types, different data sets, and different kind of realms of problems, and and so I don't want to sort of say that that definitely is a way of dealing with it. It's but there are trade-offs to that. So the trade-off to sort of cutting out 0 to 10 stories is pretty much just that you've cut out 0 to 10 stories, and you're not able to kind of look at that in a comparative way. So um, you know, uh, so like I didn't ding anyone who tried to who did that. If any, like that's definitely a valid way of sort of getting around the problem of distribution. But I sort of mentioned in any comments to students who chose that you do end up with a trade off there. Any other questions on that? Cool. So, so for the next question, the next question was dealing with a pretty new package called Data Shader, and this was a bit more focused on just kind of trying a unique example using Data Shader to kind of get the basics of how the package works. And so with the first question, we're kind of dealing with the limitations of dealing with large data sets. So when you're looking at these large data sets, it's hard to really show everything at once. So you resort to different different tactics in terms of binning and aggregation. So here, you could kind of think of things like histograms, 2D histograms. So here, this is a 2D histogram looking at height versus year, and like these are kind of some strategies of dealing with it. But what Data Shader does is it kind of does away with that need to actually bin your data. Packages like Plotly or other really any other graphing package, Matplotlib, Seaborn, ggplot, they all really they essentially treat what you're plotting as if it's infinitely resolvable, and it kind of uses a one-size-fits-all algorithm to just say, I'm drawing lines from this point to this point, I'm plotting points here. And what Data Shader is doing is it's really saying, we're looking at this through a screen. These screens have pixels, and and in addition, there's inherent limitations to just what you could see. Given these limitations, what is the best way to display these dense region, sort of a very dense data sets? So looking at something like this, it's sort of doing a few things. When you do have when you do have sort of dense regions, it's coloring the points based on how dense those points are, and kind of stacking them all together, and then kind of dispersing them as you get into sparser regions. Really, that's kind of what Data Shader is all about. There are a few other packages that deal with big data. So in previous iterations of this course, we used a package called BigViz, which is created by Hadley Wickham and for R, and this is meant to plot large data sets, and it's similar to Data Shader in that it tries to provide kind of an automatic way of plotting large data sets, but it's still based in the bin and aggregation mindset. So looking at what you're doing with BigViz, you end up with things like, so here, for example, we're binning, this is the same data, the Pluto data. We're binning the data by every 5 years, where it gives you the option to include sort of other measures. So in this case, we're looking at lot area, and that's what's coloring that. That's what's coloring that here, and BigViz relies pretty heavily on sort of automatic plotting. So it sort of lets you condense and bin the data however you want, and sort of come up with a plot that makes sense given what you've done. And this is kind of in contrast to data shader, where data shader is a bit lower level, where you're throwing in sort of your points and sort of defining your X, your Y, your various categories, and the automation is happening with how the data is being presented rather than how you're aggregating the data. So here, for example, like this is a singular sort of binning, but you're able to do two-dimensional binning. So here, this is a movies data set, and we're binning by length as well as rating. And here there are just some wonky, very long movies, but it includes some helpful built-in functions like peel here to sort of get rid of those outliers. And this, so really what's happening is it's providing you sort of a contextual binned visualization type, in this case a 2D histogram, that makes sense given how you condensed and binned the data. So I chose not to go with this because it's you can see it hasn't really been maintained in a while, and data shader is a really cool package. So I wanted to make sure that it's new. It's only, I believe, like a year and a half old, but so it's still rough around the edges. But I think this is really something that is, as time goes on, going to be really coming more into focus. So one thing I mentioned is, as you're looking at this, you have scatter plots, but data shader also shines with geographic information. So looking at latitudes and longitudes with data sets that are very densely packed, you end up with kind of sort of a very high resolution sort of geographic heat map. So here, this is just naively plotting the Pluto data set, which is actually kind of interesting because it's giving us only the density of structures. So it's kind of showing us not as many lots in Manhattan, where actually things are denser, because a taller building is taking up a wider lot, and you're going to have more people packed there, but you're going to have fewer lots. So that's kind of why you have a dearth of buildings here, and you really see denser buildings in kind of the sort of ring around Manhattan, sort of the brownstone belt. So the second question, we were looking at, sort of pretending you're a real estate developer and researching underbuilt areas of the city. So in Pluto, you have both assessed land and assessed total, and you're sort of looking at you're sort of using this as a rough measure of which areas are overbuilt versus underbuilt. So whenever you kind of are reasoning that as land is getting more expensive, you're going to build denser, you're going to build more densely there. Therefore, the structures that you're building are going to be you're going to build taller buildings. You're going to have more structure built there. And one measure of looking at sort of what could be underbuilt versus overbuilt is if the land is expensive, but the value of the structures built on that expensive land isn't as much as sort of is more is priced too low. So that would be sort of an opportunity for a developer to sort of build more densely there. So something like this, I really wanted to have, this was meant to be more of a kind of, a sort of something to get your head around data shader, and was meant to be sort of an interesting use case that shouldn't be sort of as involved to implement, but just something that kind of makes you think about what the question is asking. So here I'm sort of I ended up providing the link to a bivariate distribution, bivariate choropleth maps, and sort of using this strategy to look at these two variables. And so we kind of have a complex scale that we're using, but for the purposes of data shader, all we're doing is really looking at things categorically. And most people ended up coming up with something similar to this, where you have sort of divide the buildings into 3 percentiles, and 3 percentiles each, for assessed total and assessed structure, and thus come out with 9 different categories. So just 3 times 3. And so most people ended up arriving with something similar to this, with a few key exceptions that I'll go through. And the map that you end up with should be something that looks like this. So you have and this highlights sort of some problems with data shader. So it's like, obviously creating something like this is amazing, so that you're able to properly color something like this with the points being so dense. But data shader fails a bit in terms of being able to label something like this. So that's just sort of one thing that I'm hoping that as data shader evolves, it'll kind of be a bit further integrated into Bokeh, and kind of really allow sort of more more visualization there. And Dubar mentioned that. And actually, Dubar, I believe it was you who posted these videos in the discussion boards. So thank you so much for posting those, because I actually, Peter Wang and James Bednar are the creators of Data Shader, and it's so like when I was trying to find documentation, I was finding it a bit lacking, but the videos really really help to sort of be an additional resource. So thank you for posting that. And the so that's sort of just what I found as one drawback. But obviously you're able to something like this, you're able to get a really granular view of what's happening here. So what we end up seeing, the greener areas are, and I just wrote myself kind of a comment here, greener areas are higher value of assessed land. Redder, and that should be structure. Redder area is sort of a higher value of assessed structure, and maroon is higher values of both, and white, sort of whiter areas, are lower values of both. So you kind of have you have sort of these areas in closer to the city, where the land is sort of more expensive relative to the structures. These areas kind of in central Brooklyn and southeastern Queens, where perhaps areas are overbuilt. Some areas in the Bronx where it's both structures and land are cheaper, and then Manhattan, where it's properly built. It's very dense. The structure, the structure values are high, and the land values are high. And looking at something like this, really this gives you a lot of information. And just one thing, a few things I want to mention about some pitfalls that students ran into. A few students chose to, rather than look at a bivariate scale, look at these scales as ratios. So, and this was absolutely valid. I didn't, like any of these alternative ways of looking at it, I really didn't, really mark down. I just, really this was just meant to sort of play with data shader. So when you're looking at these as a ratio, you would absolutely get a lot of the information that's being shown here. So, really what you would see is you would see green area. So, you would see green areas on one end of your spectrum. You would see these red areas showing up on the other end of the spectrum. Maroon and white areas would show up in the middle. But what you're losing out on, you're getting a lot of that information, but the as you could see with the maroon versus white distinction, you wouldn't be getting that if you were purely looking at a ratio. So if we did plot out just the ratio, you would get you would not see that distinction between these white points and these maroon points. They would both be in the middle of your scale and would kind of show as being properly built. So that was one sort of alternative that I noticed students used. And a few students ended up using sort of looking at this as two separate data sets, and then using data shader to kind of plot both of them on top of each other. And so this is an example of one student who chose such a method. And I still need to sort of dig into what exactly is being shown here. I'm pretty sure what's being shown is so first of all, just to kind of go through what this student did, they created two separate canvases and two separate aggregations, and ended up stacking them together. So having this structure and land, stacking them together. So that's comparable to this, like when we're looking at plotting pitfalls, that's comparable to these examples here, where you have two data sets, you're trying to plot them together. The order of plotting them shouldn't be sort of controlling what the visualization looks like. And data shader solves that by having an algorithm that sort of prevents that from happening. So these two look the same, as they should. But what's happening here is, and I'm pretty sure what's happening is so you have these two data sets, and the difference between these colors is really only sort of showing the differences between. So actually, structures are being included as blue and red, whereas land is being shown as green. And you'll notice there's not much green showing up here, because I think this is just kind of a one-to-one. The points are just sitting on top of each other. So I don't know exactly what the algorithm is doing with that green, but it's not really giving us any meaningful information. Yeah, Dubar mentioned that the top color is taking over. I'm pretty sure that's like, I want to say that's what's happening because you see that blue and red, but I imagine because I think it's got to be more complex than that, because data shader has no conception of what's the top color versus the bottom color, or theoretically it shouldn't. I'd have to try out seeing if there's a difference between putting the green and blue scale, for example, above the red and blue. I didn't really have a chance to play around with that, but but either way, it's not giving us the information that we're looking for. And
I see that there is two blues
Uh-huh.
one for the structure and one for the land. So glue is used in two different things.
Mm-hmm. Mm-hmm. Yeah, so that's and actually that brings me to, so absolutely some of these blues could be coming from the second data set. And that brings me to another another thing that's happening here, which is we're kind of mixing up our aggregation scales. So you have two separate data sets here. So in that way, it's sort of showing categorical data, but each of those data sets also have their own numeric scale, and something like that. It's like I find it hard to really imagine a situation where that wouldn't really just be visually confusing and would not I think and again I haven't really tested it out that much with data shader, but I don't know if that just outright breaks it or if it's just kind of uh, not the best practice, but data shader is handling it anyway. But either way, um, this isn't the isn't really bringing us the best way of viewing this. Um, and we're approaching the end here, and I did want to make sure that we get some Shiny in on this lecture. So I'll just kind of cut off what we're talking about with data shader. But if you do have any questions, sort of chat it in, and I'll deal with it, and I'll address it after we talk about Shiny. So with Shiny, I mentioned I was going to post a few videos, or I was going to post a video, but the video that I had created from previous iterations of this class is a bit out of date, and I wanted to use the meetup to really serve as the where we're getting this information on Shiny. So I'll post this recording, and you'll be able to sort of use this to sort of get some more information on Shiny. And Kumudini asked if I could post the solutions. I didn't post them yet, but I will post them. I'm not sure if I'll post them to the GitHub or if I'll just kind of provide a sort of answer key repo. But I'll find a way to post those, and I'll put out an announcement where you can see the solutions. So to get on Shiny, with Shiny we're moving into more interactive, data-driven web app development, and Shiny is a framework that lets you purely use R to build not just kind of interactive visualizations, but really, you're building web apps. The controls that you would find in a Shiny app are really the same controls that you would find in any real web development sort of application. And I have a few test Shiny apps that will just sort of review some concepts of Shiny. And Shiny is, each Shiny app has two main. Yep, and Dubar posted a link to the main Shiny page. Shiny has awesome documentation, so I would I'd recommend checking that out as you're learning Shiny. And this is really just meant to kind of provide a brief intro to Shiny, and then provide some context to sort of subjects that we'll move on to later in the course. So each Shiny app has two main components. You have a what's called a UI component and a server component, and this dovetails pretty nicely with kind of the two sides of any web app. You have what's called a client side and a server side. And and really what this means is if you're building a web app, so I'll just get there we go. So this is kind of a toy housing price explorer. And, when you're when you're thinking of, sort of the client side versus the server side of a web app, client side is whatever is showing up in the browser and or is calculated within the browser. And server side means you're essentially, using an external resource. Usually you're using a server, so you're not using your computer to calculate what's happening. And when you have a Shiny app, so if you're just running a Shiny app from RStudio, it's all being ran on your computer. Like you could see, it's like this 127.0.0.1. That's your that's localhost. So really, that's something is running on your computer, and you're able to access that server from a browser. So it's technically all on one computer, but there's still this is still representing the server. And when you're thinking of client versus server side, client side is these sort of the display that we're seeing here. So these drop downs, this graph, this text element here, and it's also sort of what is being selected here. So the action of selecting a different metro area is something that's happening on the client side, and the server side is so if you're thinking like about a general web app, the way that you would look at it is you're sort of making selections, you're interacting with the client side of an app, and those interactions are then getting sent to the server side. So here, the client side, that's this window here, and the server side is R. So when I make a selection of a metro area, I'm filtering a data frame, and I'm using R to do that. So I have an R server that is receiving that a user selected Denver, and it's taking that information, filtering the data set, using ggplot to create a graph, and returning that graph. So so the way that that's defined with a Shiny app is the UI is just what the layout of the app is like. So Shiny uses a lot of these abstracted kind of layout features. So things like a header panel, a sidebar panel, etc. And you'll find on the Shiny site you'll find a list of all of the UI elements that are available to you. And within each of these panels, you have these elements. So you have these select inputs. These are what our drop downs are. So you have a select element for each of these drop downs, a select input rather, and you have different outputs. So you have a plot output or a verbatim text output, and that's referring to this is the plot output and this is the verbatim text output. So, and for each of these you have these strings, and these strings are serving as essentially IDs. So these come into play when you're sort of defining the logic of your app. And so in your server, this is the second part of your app is your server object. And what you're doing here is essentially defining what you want your output to be. So you have the server object itself is a function. You have your input, your output, and your session. I believe we don't use session. We're definitely not using session here, and that's a bit more advanced. But we'll just focus on input and output. And your input is referring to your input elements, so your drop downs or any other controls that you have. And your output is referring to any output elements. So in this case, your plot and your text. And all we're doing is we're using these what are called render functions to render whatever sort of output we're looking at. So if we're looking at a plot, and this plot one is tied to this ID here, so that's where that's matching. And we're representing this with a render plot function. So we're making the slice based on what we're receiving in the input. So you could see that input, these input objects that we're receiving. And using that slice, we're creating a new graph. And we're posting that graph right here. So that's what's happening in the plot. And then similarly with the stats. So again, that's tied to the ID. And we're slicing our data frame. In this case, we're also including the tier. And we're just providing a summary. So one thing to note, the graph itself, I'm only filtering the data based on seasonality and the metro area. Whereas in the text, I'm doing those two plus the tier. So in the plot, you could see you have 3 tiers that are being graphed out. So if I make changes, you could see the graph itself is changing, but the graph doesn't change if I select a different housing tier. All that changes is the verbatim text output here. So, this is a simple app, but even in this simple app, there's, sort of some kind of, sophistication going on. There's, it's not just input output. There's a bit, there's kind of some more complexity there. And I sort of think this is a good way. So I'm going to sort of go through one strategy of dealing with these sorts of interactions, which I think is useful in sort of showing, how like sort of what an app structure like this could look like. And the strategy is called reactive code blocks. So, in this app, we have a pretty simple setup. And if we look at a diagram of an app like this, we have our 3 inputs. We have seasonality, metro area, and housing tier. And we have the 2 outputs. So we have the graph and we have the input box. And you could see that housing tier is only affecting the info box, but seasonality and metro area are affecting both the graph and the info box. So in our app, this is really what the structure is. And but if you look at an app like this, and really reactive code blocks really come into play when you have some functions that are a bit more expensive than others. So one thing to imagine if this seasonality and metro area dropdowns were calling a SQL database. And whereas this housing tier, it's just filtering what's already in memory. And you may want to, be able to filter your housing tier without having, so actually to take a step back, with this app architecture, whenever you make a change to any of these inputs, you're essentially recalculating, the whole app. So if you make a change in housing tier, you're also filtering based on seasonality and metro area. So here you could see where that's happening. And perhaps the filtering by seasonality and metro area is an expensive function, and you would rather take what you've already done and only filter by tier. And the way to do that is with what's called reactive code blocks. So this is, and let me close this. This app is going to look exactly the same as the other app. And because it's such a simple app, it's going to have, the same performance. But the structure is a bit different. And so the input, the UI is exactly the same, whereas the server is a bit different. So here we just have the two outputs being defined, whereas here we have this selected data reactive function being defined. And what this is doing is it's slicing the data by seasonality and metro, and then is being referenced when we call these other two functions. So you could, and it's kind of weird. You could see it's being called as a function because the render plot is this sort of code block. So it's being called as a function, but that function is returning a data frame. So, all that function is this data frame, and we're saying we have this selected data, we're going to plot it out. Or in the stats case, we have this selected data, and we're further filtering it by tier. And looking at how that changes our architecture, we move from an architecture like this to a multi-step architecture. So here we have seasonality and metro area going into this reactive block, and then this reactive block is going into both the graph and the info box. And for a simpler app like this, there's no difference in performance, but what's happening here is if we make a change to housing tier, all that's happening is it's looking at housing tier. It's also looking at this reactive block, and it's saying, okay, seasonality and metro area didn't change, so I'm just going to use the same data that's in that reactive block to feed in the info box. And this kind of like in terms of what you're actually doing, this is a bit more logical of a layout. You have your seasonality and metro area kind of controlling your reactive block, and your housing tier is kind of a filter that's on top of that. It's sort of a nested style flow that's happening there. So in one way, it's kind of a better, like sort of just better for organization purposes. But usually where you would use something like this is if you have a very complex app and you have expensive calculations that you want to sort of bring in your data from SQL, and then you want the user to interact with it without having to continually make these expensive pulls. So I brought this up. It's for the sorts of apps that you're working on with Project 3, it's definitely not it's definitely not necessary and absolutely not required. So you don't need to add a reactive block, but I do think it helps to kind of give you an idea of how these apps are structured and like the sorts of things that you're going to begin thinking of as you sort of move on with Dash and then potentially D3 and JavaScript. So that's pretty much it I had on Shiny. Are there any questions on what I went through?
I think on my end, you clarified a couple of questions that I had. So it's good to understand a little bit more.
Cool. Yeah, Dubar, that was your second time hearing that, right?
Yes.
Cool. Cool. So I'm glad that clarified things, and that's pretty much it. So one thing, just in terms of course housekeeping, I didn't post this yet, but I'm going to post it either later today or tomorrow. But your final project proposals are going to be due along with Project 4. So it's going to be about 3 weeks from now that the proposals are due, and I'll provide the information of what's needed in an announcement. But really, what you should have in a proposal. It's just make sure that you have your data set, you know what kind of data you're going to use, and try to explain a bit like what your kind of visualization strategy is. So, kind of the common theme of this course is data visualization as, communication. So it's not enough to just simply say, I'm using this data set, but, you need to kind of go through like what you're intending to show. So if you have, if you're looking at the, using some previous data sets as an example, if you're looking at the Fortune 100 data set, it's not enough to just say, I'm going to be using this data set, but, you're going to want to say, I'm going to use this data set to show different trends in employment across different industries, or, or something along those lines. So what I like to do is with the proposals, I'm going to provide a lot of feedback. And for Project 6 is really going to be in service of your final project. So, your final project is meant to be a larger interactive visualization, and Project 6 is really meant to be a piece of that. So it's, sort of a preliminary visualization based off of your proposal. And what I like to do is kind of, look at the proposal, see what work needs to be done to flesh out a project, and try to provide guidance to sort of use Project 6 as kind of your second waypoint in the final project. The final project is worth 50% of the grade, so it's definitely, I like focusing on, sort of making sure that we have several points in the way that we're making sure that that you're able to make sure you're on track. So that information will be forthcoming. And Dubar asked another question about so Dubar, is this question about Shiny, like about R Markdown? Is this the?
Yeah, it's basically if I can present one R Markdown with the two Shiny apps inside inside the file.
Mm-hmm. Are you able to? I actually didn't even realize you're able to embed Shiny apps in R Markdown. Is that?
Yes, I've been able to do it. So that's why I'm wondering if I can do that.
Yeah, absolutely. That's actually something I haven't come across. So so go for it. Yeah.
Okay, thank you.
And Georgia asked about the structure of what's being submitted. I forget who, and Pavan asked this as well. So for going back to assignment 3, I forget who posted this in the discussion boards. But so basically, the previous Shiny used to you used to need to have a UI.R and a server.R. So, your UI would be like this would be in one file, this would be in another file, and each app would be sort of a combination of those two files. And this person who posted in the discussion forums let me know that in newer versions of Shiny, our studio is now recommending that you sort of include everything in one app, which honestly I think is a better layout. You're able to sort of not get into any trouble with sort of the scope of your app. So so either way you're comfortable with. Like it's if you want to submit a separate UI and server, or if you want to submit a singular app.r, I'll accept either of those. And also I'll accept any, like if you want to have an app for each question, or if you want to combine the two questions into one app. Really you guys are free to choose however you want to do that. So the only thing is make sure that it's clear sort of what you're doing. So if you are if you're making two separate apps with a UI and server.r, for example, make sure that you have like just send over a zip file with or send me the GitHub. Just add it in your GitHub repo this way, where you just have a folder for each app, just to sort of keep things organized.
Can we post this one in our pubs or not?
Yeah, actually, if you can, that's another thing I didn't realize you were able to do. So if you're able to so our pubs or Shiny, what is it? Shiny Studio, or shinyapps.io. That's it. If you're posting it there, absolutely feel free to send those links.
Thank you.
All right. Cool. So that should be it. Any other questions before we go? All right. So thank you everyone for attending, and hope you have a good night. Good night. Thanks.